this is what the subjects I'm going to talk about. In the beginning, I will shortly introduce the company and then just set some basis about the ORC technology so that we all have the same understanding. For some it might be boring, for other maybe it is new, but just to be part of this presentation. And then I take the turn and specifically talk about how we can apply this technology to the pyrolysis or biochar industry. And then also give some examples where we have already executed projects, or how we have incorporated that. Some more references. I will see what the time will allow, or maybe we just quickly go over, but then you have it later on probably as part of the presentation, and just a summary at the end. So the company Durr, we are a German-based company. We are in the south of Germany, southwest of Germany. Here mainly I focus on the division Clean Technology Systems. We are around about 1,400 people worldwide. And we are currently, in fact, in transition. So we are still owned and have been owned by Durr. Now there is an US-based investor who will take over 3/4 of the shares. So this is in transition and will be executed towards the end of the year. And we are very much, all the employees, very much looking forward. We think that this will can trigger even more investments and guidance towards growth path. So, and we currently have 5 facilities in the US, and that will be clearly also, it's part of the package, so that will stay also after this transition has been completed. So, ORC technology. As I said, very basic. ORC stands for Organic Rankine Cycle. And that is similar to the known water steam cycle. So what is going on in big power plants, coal-fired power plants, for example. That is, heat is taken into that system. So the heat is the driving force. The heat is, energy is transferred to the ORC working media. It is heated up and evaporated. And this vapor is then sent towards an expander. It can be a screw type of expander or a turbine, what it is in our case. And then afterwards, work has been performed. The shaft power is transformed into electricity. But it is still in vapor phase at low pressure. We need to condense the ORC media in order to close the cycle. So this is the place where we take out heat again out of the system at lower temperature. And once it is liquid again, this ORC working media, with a pump we are closing the cycle. On the right-hand side is, so engineers may be familiar with that. That is the ST diagram, which basically shows the behavior of the ORC media. And again, I mentioned already, or made the comparison to water steam cycle. That is more bell-shaped. The curve has more like a bell shape. And when you are expanding, you are in the risk of entering in the mixed area where there is like water and steam, or then liquid and steam at the same time. With the ORC working media, you see it here on the side where it's 3 and 4. When we are expanding, we are always in the dry area. And this makes it somewhat unique, because it's a kind of a fail-safe mechanism in the technology itself. So it's very sure that the turbine or whatever is there doesn't see droplets, and you do not have any problems on that side. And one step further to enhance the efficiency more often, there's another heat exchanger in between, which just is an internal heat exchange between the steam, what has not yet been condensed, and the other liquid, the ORC working media, before it's going to be sent to the evaporator. So, we have here some equations, just like what are the important parameters, and that clearly is the heat input. So Q stands for heat or energy input, and that's just a multiplication of the mass flow of the specific heating value and the temperature range from cooled down from what temperature to what other temperature. And it may well be different whether you have water from where you get your thermal energy or it's gas, then you are clearly dealing with much higher volumes to have the same mass flow and the same energy in the end. And then the power, the electric power is on the right-hand upper side. That's simply then the outcome and determined by the electrical efficiency of the system. And here the law of Carnot ties in, and that basically means the higher the temperature compared to ambient temperature of your source, this in rough words determines how efficient your system can be. So if you have only 100 degrees C available, then you are somewhat limited if your outside temperature is 35 degrees in summer, degrees C. And whereas if you have a heat source with 500 degrees C, for example, simply by the thermodynamics, it's possible to have a higher, technically higher efficiency. In this graph, in the middle, in the gray part, it's again the simplified scheme of the ORC, how it works. On the left-hand side is basically the input, the heat input, and on the right-hand side is then the output of heat. And what we want to characterize here is we just show the major 4 media, heat transfer media, which are available or which are common in use with ORC. So starting on the left-hand low bottom is water, just hot water or a little bit heated water under pressure, so up to 120 degrees. The next one is steam. Then we are rather in whatever industry who has which has saturated steam left over, can be also used in ORC. Temperature-wise, we are getting up into the range of maybe between 100 clearly and 200 degrees C. And then the light blue area is that what we call higher temperature for the ORC. And the working media, the corresponding, are then thermal oil as a heat transfer media and or gas, just gas, flue gas, for example, from any process what is up front. And we distinguish here the dark blue area is what we call low temperature ORC. You, on the right-hand side is where you take out the energy out of the system. And in order to make it work, incoming low temperature, you are more or less determined, or it's necessary that you have some kind of cooling system. You try to have that as much low temperature as possible. And that means we are working with dry coolers at that end. When we have high temperature, so the heat input is with thermal oil and or flue gas, then it's a kind of different game. Clearly you can also do electricity only, and you are condensing completely and giving that to the cooling tower. Or, and this is now another option what we have, we are running the condenser at higher temperatures. So in the range of 80 to 90 degrees C, or equivalent, I guess, 150 to 200 Fahrenheit. And this kind of heat, it's quite significant because it can be up to 80% of what has been put in on the left-hand side from the heat source can be provided at the condenser as secondary heat. for subsequent purposes, and I will show some use or explain soon after. Maybe some words about the efficiency. It's also here in the boxes. With the low temperature ORC, I've put here 6 to 12%. That's really a very wide range. But when we say, okay, starting with 90 degrees C water, this is where it can technically really is the absolutely minimum for any ORC production. And then steam, we are more in the range of 12. And at high temperature ORC, we are clearly above that and slightly below 20% electrical efficiency. In the typical ORC modular sizes, when growing even bigger, we can even achieve efficiencies above 20%. So now application to the biochar industry. This is a complicated slide, and I will stay here for maybe 2 or 3 minutes and try to walk you through. So clearly in the middle is the carbonization plant. That's here at the heart. So we have some biomass entering into the system from the left. We have this thermal process. Clearly it needs some heating in what way soever, but after all it's an exothermal process. That means energy is going out. First step in form of chemical energy in the syngas, but in most systems the syngas is really used either at the very end of the reactor or in a separate combustion chamber, and is oxidized, completely oxidized. It's burned basically, and so we have an incineration there, and afterwards it's really flue gas, just as if it's a normal combustion. So that means flue gas, and clearly temperature varies on many parameters, but it might be in the range of 800 to 1000 degrees C, and then equivalent, what is it, 1500, 2000 degree Fahrenheit. So feedstock on the left, there are some just typical, it could be like waste wood, it could be also natural or natural virgin wood. And that typically has a moisture content of around about 35%. It can go in directly in these pyrolysis systems. Then you carry all the water throughout the system up to the very end, also to the stack. And it's basically leaving your system as water vapor. So you have spent a certain amount of energy and it's all there, water vapor at 400 degree Fahrenheit in your stack. For that reason, in many cases, it's decided to have a drying system there and to bring down the moisture content to something like 10, 12, 15%. What is overall more beneficial for the pyrolysis system? As I know, it also works for many in a different way, but for better yield, after all, it's for higher yields, it's better to have a lower water content. So, and you see the blue box, this I inserted here as an ORC, just as a box. And as I explained before, in this setup with the combustion of the syngas, we can take the hot gases directly. So we cool them down just a little bit in the range of 500 degrees C in order to cope with the temperature in the primary heat exchanger. But there we are giving the temperature or transferring it to the ORC, working media. This is the place where the power then is produced. And clearly it depends on various parameters, the system, how much handling system you have up front and so. But very rough numbers I give here, that around about 30% of the power what is produced by the ORC is consumed within the system or the plant itself, with all the handling from the very beginning to the very end. But still around about 70% is then really left over, which can be used for other machines on site or even sold to the grid. And as we have here the case of high temperature ORC, it is also possible to recover or to provide the secondary heat, as we call it, at the condenser. And we can use that heat, what is, as I mentioned before, 150 to 200 degrees Fahrenheit. We use that to feed the drying. So sorry, my red arrow is here a little bit shifted. So basically, where's the pointer? So basically, we are giving the heat into the dryer, belt dryers, for example. And we can use the heat for drying the material before it enters into the pyrolysis system. And so in that way, I mentioned already earlier, you really increase the efficiency of the overall plant. In many, many cases, you have a higher throughput and better results also on the carbon side. So we are lucky that we could secure already some contracts. Those three first, what I show here, they are all in Europe. So with the company Pyrex, they are also here on the exhibit hall. The investment company was here in Novo Carbo. This is a plant which is operating in Germany since around about 2 years already. Then we have another one, might not so known to you. It's they do just business in Germany and Austria. CTS is the company. Another one we have, it's under execution with the company NGE. They are also here on this conference. And now I want to dive deeper a little bit into this unit, what is currently be erected here in the US. In Utah. So there the kind of the pyrolysis, the partner, it comes from the company Carboforce, and the customer is CO2 Sync. And so Daryl is also here. We appreciate very much that you trusted us and also Carboforce and made it possible that we can execute this project here in the US. We think it's a very, very exciting project, and it has been really a pleasure to work together with Carboforce and also CO2 Sync. And we are, as I said, it's under construction and we are very much looking forward. So in the next 2 slides, I want to show what we did in order to make that possible on our side, on the ORC. Here on the left-hand side, you see that is the EN and world where we lived in Europe. And clearly here in the US, it is mainly ASME and UL norms which we have to comply with. And I will give 3-4 examples of what we did specifically. So in Europe, we had our own design for the kind of heat exchanger. We designed it according to ISO and EN, as I said, and according to the European Pressure Directive. It is set for road transportation. It has the sizes so that it fits on a truck, but basically truck delivery is what we do in Europe, obviously. Whereas here now for the US market, it is that we have to, or we designed everything to ASME standard. We switched over, we use different types of heat exchangers. They comply now, or they are of this type TEMA. Engineers may know this is a certain type or standardized type of heat exchangers. Welds are done according to ASME, and clearly it is optimized for sea transport. So it has the sizes of a 46-foot container, the rack what you see here. The other piece of equipment I want to mention here is the evaporator. The first 2 things just similar to what I said before. In Europe, again, we design it as one piece and then a little bit oversized. We transport it to site. In the projects we had so far, it's really, we handled low dust applications. Whereas here for the US, we designed it quite differently, so in several sections, and we allowed also for reserved space for probably handling any dust problem. Because it's the first time that we do it exactly for this size together with a partner. And to be on the safe side, it has been designed in this way. And also we have an integrated hopper to take care about any dust which might settle in the system. Also then the turbine, the turbo generator received the UL stamp, so that's eligible now to deliver and to put it into operation here in the US. And also on the electrical side, the entire control and electrical cabinet is UL certified. It is under construction now. On the right-hand side is what it will look like soon. And here is, we put it up as a UR code. You can scan it and register. We also have it at our booth and the booth of Cowbo Force. We plan with CO2 Sync to have open days maybe next year in April or May. And here you can kind of enroll and get the latest information on the inventor. Yeah, our product portfolio, I make this very short. We started with modules, what you have here. For this system and others, we are rather in the plant engineering type, what you see on the right-hand side. So sizes, we're starting with 250 to up to 3 megawatt. Electrical production, and this is in fact also what we just introduced this year, calendar year 2024. You see here 2 units. They are fully designed and open for sale to the market. Units which work on either thermal oil and or hot gas. And the next step is also in preparation, so we are going to a 3 megawatt unit, which will be available from next year. Then there are a couple of references which I skim over very quickly, but just to mention, we have around about 60 plus installations in our home market and also a dozen or so internationally. And these here I leave up to you for later reading and come to my summary. So what is really about is there is this problem, what we all know about dead wood, mainly in the western states, a lot of dead wood in the forests. Here is some statement I took from the Denver Post that instead of capturing CO2, it's more like these woods are meanwhile releasing CO2. And definitely we want to be part of solving the problem in offering that that an ORC in combination with a pyrolysis system is enhancing the efficiency and is basically improving the business case after all, because of the benefits just explained in this presentation. And as we have done our homework with adaptation to the US standards and norms, we are really here for offering our product to the US market. Thank you very much.
Thank you. We have time for a couple of questions. We'll hold off on the short quiz on thermodynamics until after the session. Any questions?
What sort of working fluid do you use? Is that part of what you supply, or does it need it?
Yeah.
Is that consumable?
Working fluid is just natural hydrocarbons, so not chlorine, not fluorinated. It is not proprietary, can be bought in the market, so it's similar to tolo oil, for example. And depends. Normally we take it as part of our contract, clearly, but it can be basically sourced locally, or clearly here in the US, no problem. Yeah.
Any other questions? Well, great. Thank you, Sven, and be sure
Okay.
and stop at the Durr.
Right.